We have a very special focus. We are focusing on not only stem cells, but how to turn stem cells into very specialized cells, so-called microglia cells. When I was younger, I was working on nuclear transfer cloning, the so-called dolly. The sheep was born with this technology end of the 20th century. It was a major breakthrough, and I was part of it. I was team leader later for the dolly team. And when I returned to Hungary, I was bringing this reprogramming technology, how to turn a somatic adult cell into embryo-like cells. But suddenly in 2006 there was another discovery by Shinya Yamanaka from Japan. He got a Nobel Prize for that, how to turn without oocyte, without egg, adult cells into these pluripotent stem cells. And that discovery changed my life. I started to work on this technology. In 2009 my team was the first to make Hungarian induced pluripotent stem cells, and we focused on making neurons, mini brain cells from these, first in 2-dimension, and by now we are making 3-dimensional cells. It's also very important that we can make these cells from patients, Alzheimer or autism patients. We made quite a few cell lines, and we can make these brain structures to study the disease from very early on. However, we were missing an important element as the immune cells. And the immune cells in the brain, so-called microglia cells, are very important. In early development, they help the neurons to develop and mature. In later life or end of the life, also they are involved in dementia and Alzheimer's disease. And actually they protect us from cancer or in trauma. There is also lots of involvement, but even with infections like COVID-19, microglia cells are very, very important to defend us. And with this technology now we can make from these induced pluripotent stem cells microglia cells. We can understand how they function and how they interact, especially when we are taking cells from a diseased patient, how these genetic and other factors can play a very important role.